There is a wall in the Galilee region of modern Israel, inside a reconstructed first-century dwelling at the Nazareth village archaeological site, that has been measured, not admired, not photographed for a tourism brochure, measured. On a July afternoon, with an exterior ambient air temperature of 110 degrees Fahrenheit, the interior surface of that wall, 24 inches of cut limestone, dressed by hand, set without mortar in some sections and with a crude calciumite-based morite in others, registered 77 degrees Fahrenheit. The air inside the room, a space roughly 12 feet by 10 feet with a single window opening no wider than 18 inches, measured 75 degrees. No fan, no evaporative cooler, no ductwork, no compressor cycling on a concrete pad outside, nothing mechanical, nothing electrical, nothing that could break, nothing that required a monthly payment, nothing connected to a grid. That number, 77 degrees on the interior wall face, 33 degrees cooler than the air outside, is not a historical anecdote. It is a thermal performance measurement, and it sets a standard that the average American home built in the last 50 years has never met and was never engineered to meet. Not because the physics is unknown, not because the materials are unavailable, but because the metric by which American residential construction measures thermal performance, the R value, was designed around a fundamentally different question. R value measures resistance to heat flow through a material. It answers one question: how slowly does heat pass through this wall? It does not measure how much heat that wall can absorb before it begins transmitting any warmth at all. It does not measure what building physicists call thermal mass. It does not measure phase shift, the hours of delay between when heat strikes the exterior face and when it arrives at the interior face. The limestone wall in Nazareth has an R value of approximately 2.4. By modern American code standards, that is catastrophically low. A 2x4 stud wall with fiberglass batt insulation, the wall in a Phoenix tract house, rates between R13 and R15. On paper, the modern wall is 6 times more thermally efficient. In practice, the interior of that Phoenix tract house reaches 92 degrees within 4 hours of the air conditioning shutting off on a July afternoon. The limestone room in Nazareth has maintained habitable interior temperatures through July for approximately 2,000 years without the air conditioning ever being turned on, because it was never installed, because it was never needed. The R value did not lie. It answered the question it was designed to answer. But the question it was designed to answer was chosen specifically to make lightweight, fast-to-install, low thermal mass wall systems look adequate. It measures the wrong property. And it has been measuring the wrong property, codified into building standards, enforced by inspectors, taught in architecture schools, and used to sell insulation products for over 60 years. The wall in Nazareth does not care about its R value. It is too busy being 77 degrees. The material is limestone. Specifically, it is Turonian-age limestone from the Bina Formation, a geological layer that runs through much of the central and northern highlands of the Levant. It was quarried locally, within walking distance of the building sites in most cases, and cut into blocks using iron chisels and wooden wedges. The blocks vary in dimension, but archaeological surveys of first-century domestic structures in the Nazareth Basin consistently document wall thicknesses between 20 and 26 inches. 24 inches is the working average. Limestone is not exotic. It is calcium carbonate, the same compound found in chalk, in seashells, in the antite tablets in a bathroom cabinet. What makes it remarkable as a building material in hot climates is not its chemistry, but its physics. 3 numbers define its thermal behavior. The first is density. Limestone from the Bina Formation averages 2,160 kilograms per cubic meter. For comparison, a standard gypsum drywall panel, the interior wall surface in 93% of American homes built after 1950, has a density of approximately 650 kilograms per cubic meter. The limestone is more than 3 times heavier per unit volume. That mass is not decorative. It is functional. It is thermal storage. The second number is specific heat capacity. 0. 84 joules per gram per degree Celsius. This is the amount of energy required to raise 1 gram of the material by 1 degree. Limestone requires a significant energy input before its temperature changes. It absorbs heat slowly. It releases heat slowly. It resists rapid temperature change the way a large body of water resists rapid temperature change. Not by blocking heat, but by absorbing it into a mass so large that the temperature rise is distributed across a vast thermal reservoir rather than concentrated at the surface. The third number is thermal diffusivity, and this is the number that explains the wall in Nazareth. Thermal diffusivity describes how quickly a temperature change at one face of a material propagates through to the other face. For limestone at the density found in Nazareth construction, thermal diffusivity produces a phase shift, a time delay of between 8 and 10 hours for a 24-inch wall section. When the July sun begins heating the exterior face of that wall at 8 in the morning, the thermal wave does not reach the interior face until 4 or 5 in the afternoon at the earliest. And by then, the sun has moved past its peak angle, the exterior air temperature is dropping, and the wall's interior surface begins re-radiating its stored heat into the cooling evening air rather than into the occupied room. The wall does not block heat. It delays it. And by delaying it past the peak occupancy hours, it eliminates the thermal load that modern air conditioning systems exist to manage. The limestone is not insulation. It is a thermal time machine. It shifts the heat into a window of time when it no longer matters. That is what the wall was doing. That is what the R value does not measure. And that distinction between blocking heat and shifting heat is the central engineering difference between the house in Nazareth and the house in Phoenix. One system stores energy and releases it on a delay. The other system tries to resist energy and fails within hours, then relies on a compressor to remove the heat that got through. One is passive, continuous, and maintenance-free. The other consumes between 2,000 and 4,000 kilowatt-hours of electricity per cooling season and has a mechanical lifespan of 12 to 18 years before requiring replacement at a cost of $4,000 to $12,000. The homes of first-century Nazareth were not designed by architects. They were not reviewed by a building department. No permits were pulled. No inspections were scheduled. What they were was the product of roughly 4,000 years of continuous empirical refinement in hot, arid climate construction across the eastern Mediterranean and the Levant. The knowledge was not theoretical. It was inherited. A builder in Nazareth in the year 30 CE built the way his father built, who built the way his father built, because what they built worked, and what did not work had been abandoned generations earlier. The design logic was consistent across the Nazareth basin and can be reconstructed from archaeological excavation, from contemporary accounts, and from structures still partially intact in the region. A typical first-century domestic dwelling in Nazareth followed a pattern that addressed 4 thermal problems simultaneously. The first was wall mass. Walls were thick, 20 to 26 inches, because thick limestone walls delayed heat transmission. This was not a conscious application of thermal diffusivity equations. It was a construction norm preserved because the result was a cool room in summer and a warm room in winter. The physics was correct. The vocabulary was absent. The second was orientation. The single window, and in many structures there was only one, was placed in the northern wall or the eastern wall, never the western wall. The western face receives the most intense solar radiation in the afternoon hours, when ambient temperatures are highest and when the occupants are most likely to be inside. Placing a window in the western wall would have been the equivalent of cutting a hole in the thermal envelope at the worst possible time and angle. The builders of Nazareth did not use the phrase thermal envelope. They knew which wall got hot in the afternoon. The window went somewhere else. The third was the semi-subterranean floor plan. Archaeological surveys in the Nazareth basin, particularly the work conducted at the Sisters of Nazareth site and the adjacent Nazareth village reconstruction, document a consistent pattern of domestic structures built partially into the limestone hillside. The rear wall and sometimes one or both side walls were not constructed at all. They were the hillside itself, raw limestone bedrock, with the interior face dressed smooth but otherwise unmodified. The floor in many cases was cut directly into the rock, placing the living surface 3 to 5 feet below the exterior grade. This was not a basement in the modern sense. It was a deliberate use of the Earth's subsurface thermal stability. Below a depth of approximately 4 feet, ground temperature in the Galilee region remains between 55 and 65 degrees Fahrenheit year-round, regardless of surface air temperature. A room cut into that ground is a room with a floor and at least one wall that are permanently cooled to a temperature 20 to 30 degrees below the summer ambient air. No energy input required, no maintenance, no degradation over time. The ground temperature in the Galilee today is the same as it was 2,000 years ago. The cooling system has not needed a service call. The fourth was the courtyard. Nearly all domestic structures of this period in the region were organized around an interior courtyard, an open-air space enclosed by the walls of the dwelling and sometimes shared with adjacent structures. The courtyard was not ornamental. It was a convective engine. At night, as the desert air temperature drops, and in the Galilee in summer, nighttime temperatures can fall 30 to 40 degrees below the daytime peak. Cool, dense air sinks into the courtyard and pools at ground level. The courtyard geometry, enclosed walls, open sky, stone floor that radiates stored heat upward and away, accelerates this pooling effect. By dawn, the courtyard contains a volume of air that is significantly cooler than the ambient temperature will reach by midday. As the morning sun begins heating the exterior walls and the surrounding landscape, this pool of cool air is drawn through the doorways and window openings of the adjacent rooms by simple convective pressure differential. Warm air rising inside the room, cool air from the courtyard replacing it at floor level. The courtyard functions as a passive air handler. It collects cool air at night, stores it in a thermally buffered enclosure, and distributes it through the dwelling in the morning hours when the thermal load begins to build. No fan, no duct, no thermostat, no electricity. These 4 elements, wall mass, selective window placement, semi-subterranean construction, and courtyard convection, are not 4 separate systems. They are one integrated thermal strategy that operates on a 24-hour cycle. The walls delay exterior heat. The subterranean contact provides a constant cool baseline. The courtyard collects and distributes cool air. The window placement minimizes direct solar gain. Together, they create an interior environment that remains between 68 and 77 degrees Fahrenheit through a summer day that reaches 110 degrees outside. The system requires no energy input, no mechanical components, no control interface, and no ongoing expenditure. It has been operational for 2 millennia. It has never been serviced. It has never broken down. It has never sent anyone a bill. What happened to this system was not an accident. It was a sequence of specific decisions made for specific economic and industrial reasons over a period of approximately 150 years, each one rational in isolation. Each one removing a piece of the thermal logic that had kept human beings cool in hot climates for 4,000 years, and each one creating a dependency on mechanical cooling that did not previously exist. The first decision was the replacement of mass with frame. Beginning in the late 19th century and accelerating through the post-World War II housing boom, American residential construction shifted from masonry, stone, brick, concrete block, to light-frame timber construction. A 2x4 stud wall with exterior sheathing, fiberglass bat insulation, and interior gypsum board can be erected in a fraction of the time required to lay a masonry wall. It requires less skilled labor. It costs less per linear foot. It weighs less, which means lighter foundations, which means lower site preparation costs. On every metric that a developer uses to evaluate construction method, speed, cost, labor availability, material supply chain, the timber-framed wall wins. On thermal mass, it does not compete. It does not even participate. A standard 2x4 stud wall with R13 fiberglass bat insulation has a thermal mass so low that it reaches interior surface temperature equilibrium with exterior conditions in approximately 2 to 3 hours of sustained sun exposure. The 8 to 10 hour phase shift provided by the limestone wall in Nazareth does not exist. There is no delay. There is no buffering. There is no thermal reservoir. Heat arrives at the exterior sheathing, passes through the insulation at a rate slowed by the R value, and arrives at the interior drywall surface, and the drywall, with its low mass and low specific heat capacity, heats up almost instantly. By early afternoon on a summer day, the interior surface of a west-facing stud wall in a Phoenix home is warm to the touch. The wall is not storing heat. It is transmitting it in near real time, with a lag measured in minutes rather than hours. The insulation slows the transmission. It does not shift it. The difference between slowing and shifting is the difference between a house that gets hot more slowly and a house that stays cool until evening. One requires air conditioning. The other does not. The second decision was the abandonment of thermal design in favor of lot optimization. The courtyard vanished. The semi-subterranean floor plan vanished. Window placement became a function of street frontage and curb appeal rather than solar orientation. In a modern American subdivision, the orientation of the house is determined by the shape of the lot, which is determined by the subdivision plat, which is determined by the developer's goal of maximizing the number of saleable units per acre. Whether the largest window wall faces south, west, or directly into the afternoon sun is, in most cases, not a design consideration. It is a coincidence of geometry. The result is that a significant percentage of American homes have their maximum glazing area oriented toward the west, the worst possible thermal orientation in a hot climate. They are designed to collect afternoon solar heat with maximum efficiency, then rely on mechanical cooling to remove it. The single window in the northern wall of the Nazareth house was not an aesthetic preference. It was a thermal decision embedded in construction tradition so deeply that no builder would have thought to explain it. The floor-to-ceiling sliding glass door on the western wall of a Scottsdale tract house is also a decision. It was made to sell the house. It makes the house approximately 40% harder to cool. The homeowner pays that cost every month from May through October. The builder paid nothing. The third decision, and the one that sealed the dependency, was the industrial normalization of mechanical air conditioning as a design assumption rather than a design supplement. Before 1950, residential air conditioning was a luxury. Homes were designed with operable windows, sleeping porches, cross-ventilation pathways, shaded overhangs, and thermal mass where available. The house was designed to be habitable without mechanical cooling. Air conditioning, where installed, improved comfort. It did not provide survival. After 1960, and definitively after 1970, when central air conditioning became a standard feature in new construction across the American South and Southwest, the design logic inverted. The house was no longer designed to function without mechanical cooling. It was designed around the assumption that mechanical cooling would always be running. Operable windows were replaced with fixed glass. Sleeping porches were eliminated. Cross-ventilation pathways were closed in favor of sealed, conditioned envelopes. Overhangs were reduced or removed because they interfered with the desired aesthetic of large, light-filled window walls. Thermal mass was abandoned because it was slow and expensive to install. The house became a sealed box with a machine attached to it, and the machine became the only thing standing between the occupants and an interior temperature that would reach dangerous levels within hours of a power failure. This is the condition of approximately 89 million American homes built between 1970 and 2024. They are thermally non-functional without continuous mechanical cooling. They cannot maintain a habitable interior temperature in summer under their own thermal properties. Remove the air conditioning through equipment failure, grid outage, or inability to pay the electric bill, and the interior temperature of a standard American frame house in Phoenix, Las Vegas, Houston, or Atlanta will exceed 90 degrees Fahrenheit within 4 to 6 hours on a peak summer day. Within 12 hours, interior conditions reach levels classified by the CDC as dangerous for elderly residents, infants, and individuals with cardiovascular conditions. And the electricity bill. The average American household spends between $200 and $400 per month on cooling during peak summer, depending on climate zone, home size, insulation quality, and equipment efficiency. Across a 30-year mortgage, a homeowner in Phoenix will spend between $72,000 and $144,000 on electricity to cool a house that a 24-inch limestone wall could cool for free. That is not a metaphor. It is an accounting comparison between two thermal systems, one of which has operating costs and one of which does not. If this is the house you are sitting in right now, and statistically, for the majority of people watching this, it is, then the information that follows is not academic. There is a link in the pinned comment below this video. It contains a step-by-step thermal assessment protocol, how to measure the thermal mass of your existing walls, how to identify the highest impact passive cooling interventions for your specific structure, how to evaluate whether a thermal mass retrofit, interior mass wall, earth contact modification, or courtyard addition is feasible for your property and your budget. It is drawn directly from the documented performance data of the construction systems described in this video. It is not a product. It is not a course. It is the same engineering data reorganized as a decision-making tool for the person paying the electric bill. Because the person paying the electric bill was never given this information when the house was sold to them. And they should have been. The physics of what the limestone wall was doing can be described with precision. And that precision is important, because precision is what separates a building material from a mythology. Limestone is not magical. It is not sacred. It is not imbued with the accumulated spiritual energy of ancient craftsmen. It is calcium carbonate with a density of 2,160 kilograms per cubic meter, a specific heat capacity of 0. 84 joules per gram per degree Celsius, and a thermal conductivity of approximately 3 watts per meter Kelvin. From these three numbers, every thermal behavior of the Nazareth wall can be calculated, predicted, and replicated. The calculation proceeds as follows. Thermal diffusivity, the rate at which a temperature change propagates through a material, is defined as thermal conductivity divided by the product of density and specific heat capacity. For the Nazareth limestone, this yields a thermal diffusivity of approximately 7, 2 times 10 to the negative 7th meters squared per second, applied to a wall thickness of 61 meters, 24 inches. The time required for a thermal wave to propagate from the exterior face to the interior face is between 8 and 10 hours, depending on the boundary conditions at each surface. What this means in practice is that when the July sun begins heating the exterior wall at 8 in the morning, the thermal energy does not arrive at the interior face until approximately 4 to 6 in the afternoon. But the critical detail is not simply the delay, it is the attenuation. As the thermal wave passes through the mass of the wall, its amplitude is reduced. The peak temperature differential at the exterior face might be 40 degrees. If the air is 110 and the wall's nighttime equilibrium temperature was 70. By the time that thermal wave reaches the interior face, its amplitude has been reduced to approximately 5 to 8 degrees. The interior face might rise from 68 degrees to 75 degrees over the course of the late afternoon, a change so modest that the occupants of the room may not consciously perceive it. And then the cycle reverses. As the exterior air temperature drops in the evening, and in the Galilee in summer, nighttime lows fall to the mid-70s or even high 60s. The exterior face of the wall begins releasing its stored heat to the cool night air. By dawn, the wall has discharged a significant portion of the thermal energy it absorbed during the previous day. Its temperature profile has been reset. It is ready to absorb and delay the next day's heat load. This is a self-resetting system. It operates on a diurnal cycle that aligns with the natural temperature swing of a hot, arid climate. It does not require external energy to reset. It does not require maintenance. It does not degrade. Limestone walls in structures across the Mediterranean and Levant have been performing this thermal cycle daily for millennia. The material shows no thermal fatigue. The performance does not decline. The courtyard added a second thermal mechanism to this daily cycle, and it is a mechanism that modern residential design has not only abandoned but structurally prevented. A courtyard enclosed by stone walls and open to the sky functions as a selective radiative cooling system at night. The stone floor and walls of the courtyard, heated by the day's sun, radiate that stored heat upward toward the night sky. The sky, in a clear, arid climate, has an effective radiative temperature significantly below the ambient air temperature, in some conditions as low as -4 degrees Fahrenheit. The stone surfaces of the courtyard can cool to temperatures below the ambient air by radiating heat directly to this cold sky sink. The air in contact with these cooled surfaces also cools, becomes denser, and pools at the lowest level of the courtyard. By dawn, the courtyard contains a reservoir of air that may be 10 to 15 degrees cooler than the ambient temperature that will prevail by midday. As the sun rises and the surrounding air begins to warm, a convective pressure differential develops between the cool air pooled in the courtyard and the slightly warmer air inside the adjacent rooms. This differential drives airflow. Cool courtyard air moves into the rooms at floor level. Warmer room air rises and exits through high openings or simply through the courtyard itself. The effect is a gentle but continuous ventilation with air that is significantly cooler than the outdoor ambient temperature. This passive ventilation continues through the morning hours and into early afternoon, supplementing the thermal mass buffering of the walls with a direct supply of cooled air. The semi-subterranean design contributed a third thermal layer that is perhaps the most thermally powerful and the least replicable in modern above-grade construction. The Earth itself, below a depth of approximately 4 feet, maintains a temperature that is essentially independent of surface air conditions. In the Galilee region, this subsurface temperature is approximately 55 to 65 degrees Fahrenheit, year-round. A room carved into the limestone hillside, with its floor and one or more walls in direct contact with this stable thermal mass, has a permanent, passive cooling source that requires no energy input and that operates regardless of exterior conditions, regardless of season, regardless of whether the courtyard convection is active or the wall mass is fully charged. The ground is simply cool. It has always been cool. It will continue to be cool. And every surface of the room that is in contact with it acts as a radiant cooling panel, absorbing heat from the room air and conducting it into the infinite thermal sink of the earth below. Researchers at the Massachusetts Institute of Technology's Building Technology program and at the Technion, Israel Institute of Technology, have conducted thermal modeling studies of first-century Levantine domestic structures using modern building energy simulation software. The results consistently confirm what the physical measurements at Nazareth village demonstrate: that a structure combining 24-inch limestone walls, semi-subterranean construction, selective window placement, and courtyard ventilation maintains interior temperatures between 68 and 77 degrees Fahrenheit under peak summer conditions that exceed 110 degrees Fahrenheit at the exterior. The models also confirm that no single element of the system produces this result independently. It is the combination, mass, earth contact, convection, and solar control, operating as an integrated system on a 24-hour cycle that achieves the performance. Remove the wall mass and the system loses its delay. Remove the earth contact and it loses its baseline. Remove the courtyard and it loses its cool air supply. Remove the solar control and the thermal load exceeds the system's capacity. Every element is necessary. None is sufficient alone. This is the standard, not a theory, not a proposal, not a vision for the future of sustainable residential design. A documented, measured, physically verified performance standard that has been operating continuously for approximately 2,000 years in a climate that is thermally comparable to the American Southwest. A standard that modern American residential construction has never met. Not because it cannot, but because the materials industry, the construction industry, and the building code system that governs American housing were all organized around a different set of priorities. Speed of construction, cost per square foot, scalability of labor, and the assumption of unlimited, affordable mechanical cooling. Those priorities produced 89 million homes that cannot function without air conditioning. The limestone house in Nazareth has never had air conditioning. It has never needed it. The data is not hidden. It is published. It is peer-reviewed. It is available to any architect, any builder, any building code official, and any homeowner who wants to read it. Thermal mass construction methods, including modern adaptations using rammed earth, insulated concrete forms, autoclaved aerated concrete, and phase change materials embedded in conventional wall assemblies, are fully engineered, fully documented, and commercially available today. They are not fringe. They are not experimental. They are simply not the default, because the default was established by an industry that profits from selling both the walls that fail and the machines that compensate for their failure. What remains is the wall. A section of first-century limestone in the Galilee, 24 inches thick, its exterior face bleached and pitted by 20 centuries of sun and rain, its interior face smooth and cool to the touch at 3 o'clock on a July afternoon. 77 degrees, no wires, no ducts, no compressor, no monthly payment. The number does not argue, it does not persuade, it does not advocate for a return to anything or a rejection of anything. It simply sits there, on the interior face of a 2,000-year-old wall, calmly and permanently lower than the number on the thermostat of a house that costs $400 a month to keep cool. That is the measurement. That is the record. And every home built from this point forward will either meet that standard or explain, in kilowatt hours and dollars and degrees of interior temperature on the day the power goes out, exactly why it does not.